Have you ever held a smooth, cool stone in the palm of your hand and felt the strange, quiet weight of it? A weight that seems to carry not just the stone itself, but all the stories of the earth it came from. And in that quiet moment, have you ever wondered what that stone, your own hand, and even the air you are breathing are actually made of? Because if you could somehow travel into the deepest heart of any object, smaller and smaller, past the surface and into the invisible, you would find a world so strange and so beautiful that it seems impossible. A world where everything is built from tiny, dancing building blocks so small that millions of them could fit across the width of a single human hair. And in this world, there are no solid walls, no hard edges, only a vast, echoing emptiness filled with energy and motion. And this hidden universe is not just the secret of what a rock or a flower or your own body is made of. It is the secret of the stars themselves, of the sun that warms your face, of the distant galaxies that float in the darkness, and of the very beginning of time. And when we open this tiny door, we find that everything we have ever touched, seen, or loved is built from the same simple pieces, arranged in different ways, like the most beautiful and intricate puzzle in all of existence. And understanding this puzzle is to understand the deepest story of who we are and how we came to be. So let us take this journey together, very slowly, as the night settles around us, and gently explore everything about atoms, from the ancient dreams of philosophers to the most astonishing discoveries of modern science. Because this is not just a story about tiny particles, it is the story of the universe itself. The story of the air you breathe, the ground beneath your feet, the food you eat, the water that flows through rivers and oceans, the fire that gives warmth, and the very light that allows you to see the faces of those you love. Before we continue, I would love to know where you are listening from. Tell me your country, your city, and what time it is there right now. Because I always enjoy seeing how far these quiet science journeys travel around the world. And it makes me happy to know that somewhere, perhaps in a bustling metropolis or a sleepy village, you are sitting with me. Imagine for a moment that you are shrinking, not like in a dream, but really, truly shrinking, smaller and smaller. And as you shrink, the world around you begins to change in ways that are almost impossible to believe. The solid ground beneath your feet no longer feels solid. The air that seemed so empty begins to feel thick and crowded. And you realize that the world we see with our ordinary eyes is not the world as it truly is. It is just the surface of things, a kind of map that hides the incredible depths below. When you look at a grain of sand on a beach, you see a tiny, solid speck. But if you could travel into that grain, you would find that it is made of millions and millions of even tinier pieces, pieces so small that they are invisible to any ordinary microscope. And those pieces are atoms. The name atom comes from an ancient Greek word that means undividable, because the Greek philosophers who first thought about them believed that you could not break them into anything smaller. They imagined that if you kept cutting and cutting a piece of matter, eventually you would reach a point where you could not cut anymore, and that tiny, unbreakable piece would be the atom. And this idea, which was just a thought in the minds of people who lived more than 2,000 years ago, turned out to be one of the most powerful and lasting ideas in all of human history, because it pointed the way toward the truth that everything, absolutely everything we see around us, is built from these tiny pieces, and the way they are arranged, the way they connect to each other, the way they dance and move, and swap partners determines whether something is a rock or a flower or a star or a person. So atoms are not just a scientific detail, they are the alphabet of the universe, the letters that spell out every single thing in creation. Now we must be very careful here, because we are about to enter a world that is very different from the world we are used to. The world of the atom is a world of strangeness and mystery, a place where the ordinary rules of everyday life seem to break down, and where things behave in ways that are almost impossible to picture in our minds. But we are going to take this slowly, one idea at a time, so that we can understand not just the facts, but the wonder of it all. And to truly understand atoms, we first have to understand that they are not solid little balls, like tiny marbles or grains of sand. That is a picture that many of us carry in our heads from childhood, but it is not quite right. Atoms are much more like tiny solar systems, with a central core and things spinning around it. But even that picture is not quite right, and we will refine it as we go along. The important thing to hold in your mind is that an atom is mostly empty space. This is one of the most surprising and profound facts in all of science. If you could take an atom and blow it up to the size of a football stadium, the central core, which is called the nucleus, would be about the size of a small marble sitting in the middle of the field, and the rest of that huge stadium would be empty. Nothing but empty space. So when you touch a table or hug someone you love, your hand never actually touches anything solid. The atoms in your hand are repelling the atoms in the table, and you are feeling the electromagnetic force, but there is no solid contact. It is all emptiness and energy. And this idea that the solid world we experience every day is actually built on an almost infinite emptiness is a very peaceful thought. It means that we are all made of the same stuff, that the boundaries between things are not as solid as they seem, and that the universe is a vast, open, spacious place, even inside our own bodies. To understand atoms more deeply, we need to introduce a few of the characters that live inside them, and the first and most important of these characters is the proton. The proton is a tiny particle that carries a positive electric charge, and it lives in the nucleus at the center of the atom. The second important character is the neutron. The neutron is very similar to the proton in size and weight, but it carries no electric charge at all. It is neutral, like its name suggests. And the third and most light and nimble character is the electron. The electron carries a negative electric charge, and it is so tiny that it weighs about 1,800 times less than a proton. If you imagine a proton as a bowling ball, an electron would be like a tiny speck of dust spinning around it at an incredible distance. Electrons zip around the nucleus at speeds that are so fast that they are almost impossible to imagine. They are like tiny, buzzing bees dancing around a hive. And these electrons are the reason why atoms can interact with each other. They are the glue that holds atoms together, and the energy that lets them form bonds and create molecules. So an atom is a tiny community of particles, the protons and neutrons crowded together in the nucleus, and the electrons spinning in a cloud far away. And this community is held together by powerful forces. The protons and neutrons are held together by something called the strong nuclear force, which is so powerful that it can overcome the natural repulsion of protons pushing against each other, and the electrons are held in place by the electromagnetic force. The same force that gives us electricity and magnetism, and all of these forces work together to create the stable structures that we call atoms. And the number of protons in an atom's nucleus is the most important thing about it, because that number determines what kind of atom it is. It determines the element. For example, every atom that has one proton is hydrogen, the simplest and most abundant element in the universe. Every atom that has 2 protons is helium, the element that fills party balloons. Every atom that has 6 protons is carbon, the element that is the foundation of all life on Earth. Every atom that has 8 protons is oxygen, the element that we breathe every second of our lives, and every atom that has 26 protons is iron, the element that gives our blood its red color and makes up the core of our planet. So the proton number is like an atomic fingerprint, and it defines the identity of every atom. Now let us think about what it would be like to travel inside an atom, not as a scientist looking at numbers and equations, but as an explorer moving through a hidden world. If you could shrink down to the size of a tiny particle and enter the nucleus of an atom, you would find yourself in a place of incredible density and power. The nucleus is made of protons and neutrons packed together as tightly as anything in the universe, and the force that holds them together is so strong that it releases enormous amounts of energy when it is broken, which is what happens in nuclear reactions. The kind of reactions that power the sun and create the warmth and light that sustains all life on Earth. But if you moved away from the nucleus, out into the vast emptiness where the electrons are dancing, you would enter a completely different world. The electrons do not travel in fixed orbits like planets around the sun. As was once believed, they exist in what are called clouds or orbitals, which are regions of space where the electron is most likely to be found. And these clouds have very strange shapes. Some are spherical like a ball, some are shaped like a dumbbell, or even more complex shapes. And the electron is not a tiny solid ball traveling along a path. It is a wave of probability. It is both a particle and a wave at the same time, and it does not have a definite position until it is observed. This is one of the strangest and most wonderful ideas in all of science. It comes from a branch of physics called quantum mechanics, and it tells us that the universe at its smallest level is not a tidy machine. It is a world of possibility and probability. A world where things can be in two places at once, where they can appear and disappear, and where the act of observing something actually changes what it is. And this is not just a philosophical idea. It has been proven over and over again by experiments, and it is one of the deepest truths about the nature of reality. So the atom is not a simple little sphere. It is a complex, dynamic, and deeply mysterious thing. And the more we learn about it, the more we realize how much there is still to discover. To really appreciate the atom, we have to go back in time and see how human beings came to understand this hidden world. Because the story of the atom is one of the greatest detective stories in all of history. It is the story of brilliant minds working across centuries, building on each other's ideas, making mistakes, correcting them, and slowly, step by step, revealing the secret architecture of the universe. It all began with the ancient Greeks, as we mentioned earlier, with a man named Democritus. Democritus lived around 400 years before the birth of Christ, and he was one of the first people to propose that matter was made of tiny, indivisible particles. He called them atomos, and he believed that they were eternal, indestructible, and infinite in number. He also believed that they were always moving, always dancing, and that they came in different shapes and sizes, which gave matter its different properties. Democritus was a very wise man, but he had no way to prove his ideas. He could not perform experiments. He could not look through a microscope. He could only think and reason, and his ideas were brilliant, but they were largely forgotten for many centuries, and it was not until the 19th century that the atomic theory was revived and placed on a firm scientific footing. A man named John Dalton, an English chemist, proposed that atoms were solid, indivisible spheres, and that each element was made of its own unique type of atom. Dalton's ideas were so successful that they became the foundation of modern chemistry, and for the first time, scientists had a way to understand why. Substances reacted with each other in the ratios that they did. They could predict what would happen when you mixed different chemicals, and they could understand the underlying patterns of nature. But Dalton's atom was still a very simple picture, a billiard ball, and as scientists began to learn more about electricity and magnetism, they realized that the atom could not be a solid, indivisible sphere, because it contained charged particles. It contained electricity, and that meant that it had to have a structure. The discovery of the electron was a turning point in our understanding of atoms, and it happened in 1897, thanks to a brilliant scientist named J.J. Thomson. Thomson was working with cathode ray tubes, which are glass tubes with most of the air removed, and when he passed a high voltage through the tube, he observed a beam of something glowing, travelling from one end to the other. He realised that this beam was made of tiny, negatively charged particles, and he called them electrons. This was a staggering discovery. It showed that the atom was not the smallest thing after all. There was something smaller, something that lived inside the atom, and Thomson proposed a new model of the atom, which became known as the plum pudding model. He imagined that the atom was like a soft, positively charged pudding, and the electrons were like raisins scattered throughout it. It was a very creative idea, but it was not quite right, and it would not be long before another scientist would come along and blow this model apart. That scientist was Ernest Rutherford, and his experiment is one of the most famous in all of science. Rutherford and his colleagues shot tiny, positively charged particles called alpha particles at a very thin sheet of gold foil. According to Thomson's plum pudding model, the alpha particles should have passed straight through the gold with only a tiny amount of deflection. But what they saw was astonishing. Most of the alpha particles did pass straight through, but a small number were deflected at large angles, and a very few actually bounced straight back. Rutherford later said that it was as if he had fired a cannonball at a piece of tissue paper and it had bounced back, and he knew immediately what this meant. The gold atom was not a soft pudding. It was mostly empty space, with a dense, positively charged centre, which he called the nucleus, and the electrons were spinning around it at a great distance. This was the birth of the nuclear model of the atom, and it was a revolution in our understanding of the physical world. But Rutherford's model still had problems, because if the electrons were spinning around the nucleus like planets, they should gradually lose energy and spiral inwards, collapsing into the nucleus. And this does not happen. Atoms are stable. They last for billions of years, and so a new idea was needed to explain why, and that idea came from a brilliant young physicist from Denmark named Niels Bohr. Bohr proposed that the electrons could only exist in certain fixed orbits, or energy levels, like steps on a ladder, and they could jump from one step to another by absorbing or releasing a packet of energy, but they could not exist in between. This was a very strange idea, but it explained why atoms were stable, and it explained the colours of light that atoms emit. Each element emits a unique set of colours, like a fingerprint, and Bohr's model could predict these colours with incredible accuracy. The Bohr model was a huge success, and it remains a very useful way to think about atoms, even though we now know that it is still not completely accurate. The electrons do not orbit in fixed paths like planets. They exist in clouds of probability, and the quantum mechanical model that replaced Bohr's model is more accurate, but it is also much harder to visualize. So for our purposes, we can think of the atom as a tiny nucleus with electrons swirling around it in different energy levels, and those energy levels are like shells, each one holding a certain number of electrons. The first shell holds up to 2 electrons, the second shell holds up to 8, and the third shell holds up to 18. And the way the electrons are arranged in these shells determines the chemical properties of the atom. It determines how it will react with other atoms, whether it is a metal or a gas, a solid or a liquid, and whether it is stable or radioactive. And this idea that the arrangement of electrons in an atom determines its personality is one of the most beautiful and powerful ideas in all of chemistry. Now let us think about the elements, because the elements are the different types of atoms, and there are 118 known elements, ranging from the simplest, hydrogen, to the heaviest and most complex, oganesson, And each of these elements has its own unique personality, its own set of properties. Hydrogen, the number one element, is a light, flammable gas that is the most abundant element in the universe. It is the fuel that powers the stars, and it is the simplest atom of all. With just one proton and one electron, helium, the number 2 element, is also a gas, but it is inert, which means it does not react with anything. It is the element that makes your voice sound high and squeaky when you inhale it, and it is the second most abundant element in the universe. Carbon, the number 6 element, is the element of life. It is in every living organism on Earth. It forms the backbone of DNA, of proteins, of fats and sugars. It is the element that connects us to the stars, because carbon is forged in the hearts of stars through nuclear fusion, and when those stars explode, they scatter carbon across the galaxy, seeding future generations of stars and planets, and eventually, life, oxygen, the number 8 element, is the element we breathe. It is colourless and odourless and tasteless, but it is essential for life. It fuels the fire of our cells, allowing us to extract energy from the food we eat. Iron, the number 26 element, is the metal that built our civilization. It is in our blood, carrying oxygen from our lungs to every cell in our bodies, and it is at the heart of our planet, creating the magnetic field that protects us from the sun's radiation. Gold, the number 79 element, is the beautiful, precious metal that has fascinated humans for thousands of years. It is used in jewelry, in electronics, and even in medicine. And it is so unreactive that it does not tarnish or rust. And each of these elements is a different arrangement of the same 3 particles, protons, neutrons, and electrons. And it is the number of protons, as we said, that makes the difference. 1 proton is hydrogen, 2 is helium, 3 is lithium, and so on, all the way up to 118. And the periodic table, that famous chart that you might have seen in a classroom, is a map of all these elements, organized by their properties, and it is one of the most beautiful and powerful organizing principles in all of science. It reveals patterns and trends. It predicts the existence of elements that have not yet been discovered, and it shows the deep connection between all the matter in the universe. And the periodic table is not just a static chart, it is a living document that grows and changes as we discover new elements. And it is a testament to the genius of Dmitri Mendeleev, the Russian chemist who first organized the elements in a logical and predictive way. Now, we must think about how atoms come together to form molecules. Because atoms are rarely alone. They almost always prefer to connect with other atoms, to share electrons and create bonds. And this is how the incredible complexity of the world arises. Hydrogen atoms, for example, like to pair up with each other to form H2, a stable molecule of hydrogen gas. Oxygen atoms also like to pair up to form O2, the oxygen we breathe, and when 2 hydrogen atoms and 1 oxygen atom come together, they form water, H2O, the most essential molecule for life on Earth. A water molecule is a beautiful thing. It has a bent shape, like a little V, with the oxygen atom in the middle and the hydrogen atom sticking out at an angle. And this bent shape gives water many of its amazing properties. It is why water is a liquid at room temperature, why it expands when it freezes, and why it can dissolve so many substances. And this is just one example. There are billions and billions of possible molecules, from the simplest, like hydrogen gas, to the most complex, like the giant molecules of DNA that hold the instructions for building a human being. And the key to all of this is the electron. The electrons in the outermost shell of an atom are the ones that participate in bonding. They are like little hands reaching out to hold the hands of other atoms. And when atoms share electrons, they form covalent bonds, which are strong and stable. And when one atom gives away an electron to another atom, they form ionic bonds, which are also strong. And these bonds are the glue that holds the world together. They are what makes matter solid, liquid, or gas. They determine the taste of food, the color of flowers, the strength of steel, and the nature of our own bodies. And it all happens because of the dance of electrons, the endless, beautiful dance of tiny particles that creates the vast, complex, and stunningly beautiful world we inhabit. And this dance is governed by the laws of quantum mechanics, which are the laws of the very small. And they are the laws that make chemistry possible. And chemistry is the science of molecules, the science of how atoms combine to create everything from the simplest compounds to the most complex biological systems. Let us take a moment to think about the scale of the atom, because it is very hard to imagine just how small these things are. There are about 7 octillion atoms in an average human body. That is a 7 followed by 27 zeros. It is an unimaginably large number, and yet these atoms are so small that if you lined up 1,000,000 of them side by side, they would still be thinner than a human hair. The entire human body is made of about 99% hydrogen, oxygen, carbon, and nitrogen, with trace amounts of other elements. And if you could somehow remove all the empty space from the atoms in your body, you would shrink down to a tiny speck that you could barely see with a microscope. And yet this speck would still contain all the mass of your body, because the nucleus is where almost all the mass is. The electrons contribute almost nothing to the weight of an atom. They are just tiny, weightless dancers spinning around the heavy, dense nucleus. So the next time you stand on a scale and look at your weight, remember that most of that weight comes from the protons and neutrons in the nuclei of the atoms in your body. And those protons and neutrons are themselves made of even smaller particles called quarks. So the atom is not the end of the story. It is just the beginning of a journey into the very heart of matter. Quarks are fundamental particles, which means they cannot be broken down into anything smaller, as far as we know. And there are 6 types of quarks, and they combine in different ways to make protons and neutrons. So the atom, which was once thought to be the smallest, most basic unit of matter, is actually a tiny galaxy of particles. And those particles are themselves made of even tinier pieces. And this is one of the deepest and most profound lessons of modern science, that the universe is layered like an onion, and the deeper we look, the more we discover, and the more we discover, the more we realize how much we still do not know. And this is a wonderful thing, because it means that science is a never-ending adventure, and there will always be new mysteries to explore and new wonders to discover. And this journey into the heart of matter is one of the most exciting and rewarding journeys we can take. Now let us think about the atom and its connection to light, because we talked about light in another journey. And now we can see how light and atoms are deeply connected. Light is produced by atoms. When an electron in an atom jumps from a higher energy level to a lower energy level, it emits a packet of energy, a photon. And that photon is light. The colors of light we see from a flame or a star are the fingerprints of the atoms that produce them. Every element emits a unique spectrum of light, a pattern of colored lines that is as distinctive as a barcode. And by analyzing the light from a star, we can tell exactly what elements it is made of. We can tell whether it is rich in hydrogen or helium, whether it contains carbon or oxygen or iron, and we can even tell how fast it is moving, and how far away it is, because the light from a star is stretched or compressed by its motion. And this is how we have learned so much about the universe without ever leaving our own tiny planet. The atom is like a tiny bell that rings with its own unique sound, and the sound is light. And by listening carefully to that light, we can hear the whole symphony of the cosmos. And this connection between atoms and light also has practical applications. It is the basis of lasers and fiber optics and LED lighting and many other technologies that we use every day. And it reminds us that the invisible, microscopic world of atoms is not separate from our everyday lives. It is the very foundation of everything we do, everything we see, and everything we are. And when we understand this connection, we see that the universe is not a collection of separate things. It is a unified whole, and light is the thread that weaves it all together. To understand atoms even more deeply, we have to grapple with the strangeness of quantum mechanics, because quantum mechanics is the language of the atom. It is the set of rules that governs the behavior of particles at the smallest scales, and those rules are very different from the rules that govern the large-scale world. In the quantum world, particles can be in two places at once, a phenomenon called superposition. They can tunnel through barriers that would be impossible to cross in the ordinary world. They can be entangled with each other in such a way that what happens to one instantly affects the other, even if they are millions of miles apart, and the act of observing a quantum system changes its behavior, which is a very strange and unsettling idea, but it is also one of the most confirmed facts in all of science. The quantum world is a world of probability and uncertainty, where we can never know both the position and the momentum of a particle with perfect accuracy. This is called Heisenberg's uncertainty principle, and it is not just a limitation of our instruments. It is a fundamental property of the universe, and the atom, with its electrons dancing in clouds of probability, is a perfect example of this quantum weirdness. The electron does not follow a definite path. It is everywhere and nowhere at the same time, and only when we make a measurement does it appear in a specific place. And this is not just a philosophical curiosity. It has practical applications. It is the basis of quantum computing, which promises to revolutionize our ability to solve complex problems, and it is the basis of MRI machines, which use quantum effects to image the inside of the human body. So the strangeness of the atom is not just a theoretical curiosity. It is the engine of some of the most powerful technologies we have ever invented. And the more we study quantum mechanics, the more we realize that the universe is far stranger and more wonderful than we ever could have imagined. Now we must think about how atoms are made, and this is one of the most beautiful stories in all of science. The story of nucleosynthesis, which is the process by which atoms are formed. It begins in the very first moments after the Big Bang, when the universe was unimaginably hot and dense, and the only elements that existed were the simplest ones, hydrogen and helium, with a tiny amount of lithium. All the other elements were forged later, inside the hearts of stars. A star like our Sun is a giant nuclear furnace. It takes hydrogen and fuses it together to make helium. And in the process, it releases enormous amounts of energy, which is what makes the sun shine. And when the hydrogen starts to run out, the star begins to fuse helium into carbon and oxygen. And then, if the star is massive enough, it continues to fuse heavier and heavier elements, all the way up to iron. But iron is the end of the line, because fusing iron does not release energy. It consumes energy. And so when a massive star has an iron core, it can no longer support itself against its own gravity, and it collapses in a spectacular explosion called a supernova. And in the unimaginable heat and pressure of that explosion, even heavier elements are forged. Elements like gold, silver, platinum, uranium, and all the other elements that are heavier than iron. And these elements are scattered into space, seeding the galaxy with the building blocks of planets and life. So every atom of carbon in your body, every atom of oxygen you breathe, every atom of iron in your blood, and every atom of gold in your jewelry was forged in the heart of a star that lived and died billions of years ago. You are made of stardust. That is not just a poetic thought. It is a scientific fact. The atoms in your body are billions of years old. They have traveled across the galaxy. They have been part of stars and planets and maybe even other living things. And now they are part of you. And this connection to the cosmos is one of the most profound and humbling ideas in all of science. We are not separate from the universe. We are a part of it. We are made of the same stuff as the stars. And we are connected to everything that has ever been and everything that ever will be. Atoms are also the key to understanding the nature of matter itself, and matter comes in three main states: solid, liquid, and gas. And these states are determined by the behavior of atoms. In a solid, the atoms are arranged in a rigid, orderly pattern. They vibrate in place, but they do not move around. This is why a solid has a fixed shape and volume. In a liquid, the atoms are still close together, but they can slide past each other, which is why a liquid can flow and take the shape of its container. And in a gas, the atoms are far apart and moving freely, which is why a gas expands to fill any container. And if you heat a solid, the atoms vibrate more and more until they break free of their fixed positions and become a liquid. And if you heat a liquid, the atoms move even faster until they break free of each other entirely and become a gas. And if you cool a gas, the atoms slow down and come together to become a liquid. And if you cool a liquid, the atoms slow down even more and lock into a solid pattern. And these transitions are happening all around us. Every day, water freezes into ice and boils into steam. And it all comes back to the dance of atoms. There is also a fourth state of matter, called plasma, which occurs at extremely high temperatures, where the atoms are stripped of their electrons and the nuclei and electrons move around independently. Plasma is the most common state of matter in the universe. It is what stars are made of, and it is what lightning and neon lights are made of. But plasma is not something we encounter very often in our everyday lives, so it is enough to know that it exists, and that it is a very important part of the universe. And all of these states of matter are just different ways that atoms arrange themselves, and they are all governed by the same fundamental laws of physics. Now let us think about the force that binds atoms together, the electromagnetic force, which is one of the four fundamental forces of nature, the other three being gravity, the strong nuclear force, and the weak nuclear force. The electromagnetic force is the force that holds electrons in orbit around the nucleus. It is the force that makes atoms stick together to form molecules. It is the force that makes your hand repel the table when you press on it. It is the force that makes magnets attract and repel each other. It is the force behind electricity and magnetism and light. And it is the force that governs almost every interaction in our everyday lives. Gravity is the force that keeps us on the ground and holds the planets in their orbits. But it is very weak compared to the electromagnetic force. And the strong nuclear force is the force that holds protons and neutrons together in the nucleus. It is much stronger than the electromagnetic force, but it only works over very short distances, and the weak nuclear force is the force that is responsible for certain types of radioactive decay, and it is involved in the nuclear reactions that power the sun. So the atom is a place where these fundamental forces come together and interact, and the balance between them determines the structure and stability of matter. If the strong nuclear force were a little bit different, atoms would not be able to exist. If the electromagnetic force were a little bit different, chemistry would not work. If gravity were a little bit different, planets would not form, and life would not be possible. So the universe is delicately balanced, and the atom is at the center of that balance. And this balance is a testament to the beauty and elegance of the natural world. Now we must consider the mystery of the atom's stability, because as we mentioned earlier, if the electrons are moving, they should radiate energy and spiral into the nucleus, but they do not. And this is one of the great puzzles of quantum mechanics. The solution to this puzzle is that the electrons are not small particles moving along definite paths. They are waves, and a wave can exist in a stable pattern without losing energy, like a standing wave on a guitar string. The electron is a wave, and its orbit is a kind of standing wave, and it can only have certain frequencies which correspond to certain energy levels. And this is why the Bohr model worked. It was a simplified version of a much deeper quantum truth, and the quantum mechanical model of the atom, which is known as the Schrödinger equation, describes the electron as a wave function, a mathematical description of the probability of finding the electron in a particular place, and this wave function is the most accurate description we have of the atom, but it is also very abstract, and it is hard to picture, but that is okay, because the universe does not always have to be easy to picture, it just has to be true, and the quantum mechanical model is true. It has been tested and confirmed to incredible precision, and it is one of the greatest achievements of the human mind. It shows that the atom is not a tiny solar system. It is a cloud of possibility, a realm of pure potential, and that is a beautiful and mysterious thing to think about, and it reminds us that the universe is not a clockwork machine. It is a living, breathing, and deeply mysterious place. Atoms are also the key to understanding the elements and the periodic table, which we touched on earlier. But let us go a little deeper. The periodic table is arranged in rows and columns, and the rows are called periods, and the columns are called groups, and the elements in each group have similar properties because they have the same number of electrons in their outermost shell. This outermost shell is called the valence shell, and the electrons in it are called valence electrons. And it is these valence electrons that determine how an atom will react with other atoms. For example, the elements in group 1, which includes hydrogen, lithium, sodium, and potassium, all have one valence electron, and they are all very reactive. They want to give away that electron to achieve a stable configuration. And the elements in group 18, which includes helium, neon, and argon, all have full valence shells, and they are very unreactive. They are the noble gases, and they are content to exist as single atoms, not bonding with anything else. And this is why the periodic table is such a powerful tool. It not only organizes the elements, it also predicts their behavior. It reveals the underlying patterns in nature, and it shows the deep connection between all the elements. It is a map of the building blocks of the universe, and it is a testament to the power of human curiosity and intelligence. And the periodic table is still evolving. New elements are being discovered and created in laboratories, and each new element adds a new piece to the puzzle, and who knows what new elements might be discovered in the future. Maybe there are elements out there in the universe that we have not yet imagined. Maybe there are islands of stability where super heavy elements might exist for long periods of time. And maybe those elements have properties that we cannot even dream of. The atom is a doorway to infinite possibilities. Now, let us think about the atom's role in our own bodies, because the human body is a beautifully complex machine, and it is made entirely of atoms. We have billions and billions of them, all working together in perfect harmony. Hydrogen atoms are in the water that makes up most of our bodies. Carbon atoms are in the molecules that store our genetic information and provide us with energy. Oxygen atoms are in the molecules that transport oxygen to our cells and carry away waste. Nitrogen atoms are in the proteins that build our muscles and organs. Calcium atoms are in our bones, making them hard and strong. Phosphorus atoms are in our DNA and in the molecules that store energy. Iron atoms are in our blood, carrying oxygen, and sodium and potassium atoms are in our nerves, allowing us to think and feel, and every single one of these atoms was once part of something else, maybe a plant, maybe a rock, maybe a star, and now they are part of you, and when you die, those atoms will return to the world. They will be recycled. They will become part of new plants and animals. They will become part of the soil and the air and the water, and they will continue their journey through the universe, a journey that began at the dawn of time and will continue until the end of time. We are temporary arrangements of atoms, beautiful and brief, and we are connected to everything that has ever been and everything that ever will be. This is a very peaceful thought. It means that we are not isolated individuals. We are part of a vast, interconnected web of life and matter, and the atoms that make up our bodies have been on a long and incredible journey. A journey that we are only just beginning to understand. And this journey is one of the most amazing stories ever told. We cannot leave our journey without thinking about the mysteries that remain, because although we have learned an incredible amount about atoms, there is still so much we do not know. We do not fully understand the nature of the quantum world. We do not know why there is something rather than nothing. We do not know what dark matter is. We do not know if there are other universes or other dimensions. We do not know the ultimate fate of the universe. And we do not know if we are alone in the cosmos. These are the big questions, the deep questions, and they are questions that scientists are working on every day. They are building bigger and more powerful instruments. They are designing more sophisticated experiments. They are using the power of computers to simulate the behavior of atoms and molecules. And they are slowly, step by step, uncovering the secrets of the universe. And perhaps one day we will have answers to these questions. Or perhaps we will find that there are limits to what we can know. Either way, the journey is the important thing. The journey of exploration and discovery, the journey of asking questions and seeking truth, and the atom is at the heart of this journey. It is the key that opens the door to the deepest mysteries of existence, and it is a reminder that the universe is a place of infinite wonder and beauty, and we are lucky to be a part of it. Let us think about the atom in our everyday lives. Because even though we usually do not think about atoms, they are everywhere. They are in the air we breathe, the water we drink, the food we eat, the clothes we wear, and the screens we look at. Every time we turn on a light switch, we are using the principles of electricity, which is the flow of electrons through a wire. Every time we use a computer, we are using the properties of semiconductors, which are materials that have special electronic properties that allow them to control the flow of electricity. Every time we take a picture with a camera, we are capturing photons, which are particles of light emitted by atoms. Every time we listen to music, we are hearing sound waves, which are vibrations of atoms in the air. Every time we feel the warmth of the sun, we are feeling the energy released by nuclear reactions in the sun's core. Atoms are the fundamental building blocks of all of our technology, and they are the key to understanding how the world works. And when we understand atoms, we understand not just the world, but ourselves, because we are made of atoms, and we are products of the same cosmic forces that created the stars and the planets. And this understanding brings a sense of peace and connection. It reminds us that we are part of something larger, something deeper, and something infinitely more beautiful than we can fully comprehend. So the next time you look at a flower or a tree or a person you love, remember that you are looking at a collection of atoms arranged in a way that is unique and precious. And remember that those atoms were forged in the heart of a star and that they are connected to the entire universe. At this point in our journey, we should reflect on the amazing progress that humanity has made in understanding the atom, from the ancient Greeks who first dreamed of invisible particles to the modern scientists who can manipulate individual atoms and create new materials. It has been a long and winding road, filled with brilliant insights and surprising discoveries, and it is a road that is still being travelled every day. Scientists around the world are making new discoveries about the atom and its behaviour. They are finding new ways to use atoms to improve our lives, and they are pushing the boundaries of our understanding. And this is a wonderful thing, because it means that the story is not over. There are still new chapters to be written, and you are part of that story, even if you are not a scientist, because you are made of atoms. And you are part of the universe, and your curiosity and wonder are part of what drives humanity forward. So let us celebrate the atom, this tiny, invisible, and yet incredibly powerful thing, and let us continue to explore its mysteries with open hearts and open minds. For the atom is not just a scientific concept, it is a symbol of the beauty and complexity and wonder of the universe. And it is a reminder of our own smallness and our own greatness, all at the same time. And that is a beautiful thing to hold in your heart as you drift off to sleep. As we near the end of this long and gentle journey, let us return once more to the idea that everything is connected, because this is the deepest lesson of the atom. The atoms in your body were once part of other things. They have been in the hearts of stars, in the depths of oceans, in the breath of ancient animals, and in the soil of distant lands, and they will continue their journey long after you are gone. They will become part of new things, new life, new worlds, and they will carry the memory of your existence into the future. This is a comforting thought. It means that we are never truly separate. We are never truly alone. We are woven into the fabric of the universe, and our atoms are part of an eternal dance, a dance that began at the beginning of time and will continue to the end of time. And in that dance, there is peace and beauty and meaning. So let us rest in the knowledge that we are made of star stuff, that we are connected to all things, and that we are part of a story that is larger and more wonderful than we can ever fully understand. Let this thought carry you gently into sleep. Let it quiet your mind and soothe your spirit, and let it fill you with a sense of wonder and gratitude for the gift of existence, for the miracle of atoms, and for the beauty of the universe. Thank you for joining me on this journey. Thank you for your curiosity and your patience. And I hope you have found some peace and relaxation in these words. May your dreams be filled with the gentle light of 1 billion stars, and may you wake up tomorrow feeling refreshed and connected to the world around you. Good night, and sleep well, knowing that you are made of atoms, and that atoms are made of dreams, and those dreams are woven from the same fabric as the stars themselves. Yet the story is far from complete, because we have only just begun to scratch the surface of the vast and wondrous world that lies hidden within every speck of dust, every drop of rain, and every beat of your own heart. For if we look deeper still, we find that atoms are not isolated, lonely particles floating in the void. They are part of an intricate and beautiful web of interactions. A cosmic dance that connects the smallest quark to the largest galaxy. And this dance is governed by laws that are both simple and profound. Laws that have been written into the very fabric of the universe since the moment of its birth. And as we continue our journey, we will explore not just what atoms are, but what they mean, and how they have shaped the world we see around us and the world within us. For the atom is a mirror in which we can see ourselves, a tiny reflection of the grand and mysterious universe that gave us life. And as we drift deeper into this quiet night of understanding, let us hold on to the simple truth that we are not visitors in this universe. We are made of it. We are its children, its eyes, and its voice. And through us, the universe is finally beginning to understand itself, and that is perhaps the most beautiful and peaceful thought of all. Now, to truly appreciate the atom, we must understand the concept of energy levels, because these energy levels are like invisible ladders that electrons climb and descend, and each rung on that ladder represents a specific amount of energy that an electron can have, and when an electron is on the lowest rung, we say it is in its ground state, which is its most stable and comfortable position, like a person resting quietly in a cozy chair after a long day. But when an electron absorbs a packet of energy, perhaps from a passing photon of light or from a collision with another particle, it can jump to a higher rung, a higher energy level, and when it does that, we say it is in an excited state, like a person who has just had a cup of strong coffee and is feeling full of energy, and this excited state is not permanent. The electron will eventually release that extra energy and drop back down to a lower level, and when it does, it emits a photon of light, and the color of that light depends on how far the electron has fallen, how big the jump was, and this is why different elements emit different colors of light, because each element has a unique set of energy levels, a unique ladder, and the electrons in each element can only make certain jumps. So the light they emit has certain specific wavelengths, which we see as specific colors, and this is the basis of spectroscopy, which we talked about earlier. And it is also the reason why neon signs glow with such beautiful, vivid colors, because the neon atoms inside the glass tube are being excited by an electric current, and their electrons are jumping up and down, emitting photons of light that are characteristic of neon. And this is also why fireworks are so colorful, because different metals are used to create different colors. Strontium gives a brilliant red, copper gives a bright blue, sodium gives a warm yellow, and each of these colors is the signature of the atoms inside the firework, singing their own unique song of light. And this knowledge, this ability to read the light from atoms, has given us the power to understand the composition of stars that are trillions of miles away, and it has given us the power to create technologies that would have seemed like magic to our ancestors. Let us also think about the way atoms bond with each other, because bonding is what creates the incredible diversity of the material world, and there are several different types of bonds, each with its own character and strength. The strongest type of bond is the covalent bond, which we mentioned earlier, where two atoms share one or more pairs of electrons, like two friends holding hands and sharing a secret, and this sharing creates a very stable and strong connection. And covalent bonds are what hold the atoms together in molecules like water, carbon dioxide, and the complex organic molecules that are the building blocks of life. And the strength of a covalent bond depends on how many electrons are being shared and how tightly they are held by the nuclei. And some covalent bonds are very strong, like the bonds in diamond, which is made entirely of carbon atoms, each bonded to 4 others in a perfect tetrahedral structure, and this is why diamond is one of the hardest materials known to us, because the covalent bonds are so strong and so perfectly arranged, and other covalent bonds are weaker, like the bonds in wax or rubber, which is why those materials are soft and flexible. And then there is the ionic bond, which is formed when one atom gives away an electron to another atom, like a gift. And the atom that gives away the electron becomes positively charged, and the atom that receives the electron becomes negatively charged. And these opposite charges attract each other, like the positive and negative poles of a magnet, and this attraction is what holds the atoms together, and ionic bonds are what hold together salts, like table salt, which is sodium chloride, where sodium atoms give away electrons to chlorine atoms, and the resulting positive and negative ions form a crystal lattice, a beautiful, regular pattern of alternating charges, and this is why salt crystals have such a perfect cubic shape. And then there is the metallic bond, which is a special type of bond that occurs in metals, where the atoms share their electrons in a sea of free-moving electrons, like a school of fish swimming together. And this sea of electrons is what gives metals their characteristic properties, their ability to conduct electricity and heat, their malleability, and their shiny luster. And these different types of bonds are the reason why the world is so rich and varied, why some materials are hard and others soft, why some are transparent and others opaque, why some are conductors and others insulators, and by understanding these bonds, we have been able to create new materials with properties that do not exist in nature, like plastics, semiconductors, and superconductors. Now, let us dive even deeper into the nucleus of the atom, because the nucleus is not a simple, unchanging lump of protons and neutrons. It is a dynamic and sometimes unstable place, and this instability is what gives rise to radioactivity, which is the spontaneous emission of particles or energy from an unstable nucleus. And this is a process that has shaped the Earth and continues to affect us today. There are three main types of radioactive decay, and each involves a different kind of emission. The first is alpha decay, where the nucleus emits an alpha particle, which is made up of 2 protons and 2 neutrons, which is essentially a helium nucleus. And when an atom emits an alpha particle, it loses 2 protons and 2 neutrons, and it transforms into a different element, for example, radium, which has 88 protons, decays by alpha emission to become radon, which has 86 protons, and this type of decay is relatively common in heavy elements, and alpha particles are relatively large and slow-moving, and they can be stopped by a piece of paper or even by the outer layers of human skin. So they are not very dangerous unless they are ingested or inhaled. The second type is beta decay, where the nucleus emits a beta particle, which is essentially an electron. And this happens when a neutron in the nucleus transforms into a proton, emitting an electron and a tiny, nearly massless particle called an antineutrino. And this increases the number of protons in the nucleus by 1. So the atom changes into a different element. For example, carbon-14, which is a radioactive isotope of carbon, decays by beta emission to become nitrogen-14, and beta particles are smaller and faster than alpha particles, and they can penetrate a little further, but they can still be stopped by a thin layer of metal. The third type is gamma decay, where the nucleus emits a high-energy photon, a gamma ray, and this happens when the nucleus is in an excited state, like an electron in an atom, and it drops down to a lower energy state, releasing a gamma ray, and gamma rays are very high energy, very penetrating, and they are the most dangerous type of radiation. They can pass through the human body and cause damage to cells, and gamma rays are emitted in nuclear reactions, in the hearts of stars, and in the explosions of supernovae. And they are also used in medicine to kill cancer cells and in imaging to see inside the human body. So radioactivity is both a natural and a man-made phenomenon, and it is a powerful reminder that the atom is not a static, inert thing. It is a living, dynamic, and sometimes explosive source of energy. Let us think about isotopes, which are atoms of the same element that have the same number of protons but a different number of neutrons. For example, hydrogen, which has 1 proton, has 3 naturally occurring isotopes: protium, which has no neutrons, deuterium, which has 1 neutron, and tritium, which has 2 neutrons, and these isotopes have the same chemical properties because they have the same number of electrons and protons, but they have different physical properties, such as mass and stability, and some isotopes are stable, which means they do not decay, and others are unstable, which means they are radioactive, and the radioactive isotopes are called radioisotopes, and they have many important uses in medicine, industry, and research. For example, iodine-131 is a radioisotope that is used in the treatment of thyroid cancer, because the thyroid gland absorbs iodine, and the radiation from the iodine-131 kills cancer cells, and carbon-14 is used in radiocarbon dating, which is a technique for determining the age of ancient organic materials, because living organisms absorb carbon-14 from the atmosphere, and when they die, the carbon-14 begins to decay at a known rate. So by measuring the amount of carbon-14 left in a sample, scientists can tell how long ago the organism died, and this has revolutionized archaeology and geology, allowing us to date ancient artifacts and fossils with remarkable accuracy. And uranium-238 is used in radiometric dating of rocks because it decays to lead-206 over a very long time, and by measuring the ratio of uranium to lead in a rock, scientists can determine its age, and this has given us the age of the Earth, which is about 4.5 billion years. And it has given us the age of the solar system, and it has given us a timeline for the history of life on Earth. And all of this is possible because of the atom, and its incredible ticking clock of radioactive decay. Now, we must think about the atom in the context of chemistry, because chemistry is the science of atoms and molecules, and it is the foundation of all of the material world. And at the heart of chemistry is the concept of the chemical reaction, which is a process in which atoms rearrange themselves to form new substances. And this happens because atoms are always seeking a more stable configuration, a lower energy state, and they will do whatever they can to achieve that, even if it means breaking bonds and forming new ones. And these reactions are happening all around us, all the time. When you light a match, you are initiating a chemical reaction. When you bake a cake, you are performing many chemical reactions. When you breathe, you are carrying out a chemical reaction when you digest your food. You are orchestrating a series of chemical reactions, and the energy that powers these reactions comes from the breaking and forming of chemical bonds. Because when a bond is broken, energy is released, and when a bond is formed, energy is absorbed, and some reactions release a lot of energy, and they are called exothermic reactions, and they feel hot, like a burning candle, and other reactions absorb energy, and they are called endothermic reactions, and they feel cold, like a chemical ice pack. And the study of these reactions is called thermodynamics, and it is one of the most important branches of science, because it governs everything from the efficiency of engines to the metabolism of living organisms. And by understanding chemical reactions, we have been able to create all of the materials and medicines and technologies that define our modern world. And the atom is the actor in this drama, the protagonist of this endless story of transformation and change. Let us explore the concept of the mole, because the mole is a unit that chemists use to count atoms and molecules, and it is a very large number, 6.022 times 10 to the 23rd power, which is called Avogadro's number. And this number is so large that it is almost impossible to imagine. If you had a mole of pennies, you could cover the entire surface of the earth with a layer of pennies several miles thick. And if you had a mole of grains of sand, you could fill all the oceans and deserts and still have sand left over. And yet, a mole of atoms is just a tiny amount of matter, a few grams, because atoms are so incredibly small, and this number allows chemists to measure and predict the quantities of substances involved in reactions, because they know that 1 mole of one element will react with 1 mole of another element in a predictable way. And this is the foundation of stoichiometry, which is the science of measuring and calculating the quantities in chemical reactions. And it allows chemists to make everything from fertilizers to pharmaceuticals to plastics with incredible precision. And it is a testament to the power of the atom that such a tiny thing can be counted and measured with such accuracy, and that we can use that counting to shape the material world. Now, we must think about the atom in the context of biology, because biology is the science of life, and life is built on atoms, and all living things are made of the same basic elements: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur, which are the 6 most abundant elements in living organisms. And these elements form the 4 major classes of biological molecules: carbohydrates, lipids, proteins, and nucleic acids. And these molecules are the building blocks of cells, which are the fundamental units of life. And the atom is at the heart of all of this, because the structure and function of these molecules are determined by the arrangement of their atoms and the bonds between them and the way they interact with other molecules. For example, the DNA molecule, which contains the genetic. Instructions for all life is a long chain of atoms arranged in a double helix, and the sequence of those atoms encodes the information that makes you who you are, and proteins are also chains of atoms, folded into complex three-dimensional shapes, and the shape of a protein determines its function, whether it is an enzyme that speeds up a chemical reaction, or a hormone that carries a signal, or a structural protein that gives shape and support. And all of this is possible because of the atom, because atoms can bond together in so many different ways, creating molecules of infinite variety and complexity. And life is the most complex and beautiful expression of the atom's potential. And when we study biology, we are studying the atom, and when we study the atom, we are studying the foundation of life. Let us also think about the atom in the context of medicine, because medicine has been transformed by our understanding of atoms and molecules. And this is particularly true in the field of pharmacology, which is the study of drugs and how they interact with the body. And a drug is a molecule that binds to a specific target in the body, like a receptor on a cell, and this binding changes the behavior of the cell, and it can have a therapeutic effect. And the design of drugs is a precise science, because the shape and properties of the drug molecule must match the shape and properties of its target, like a key fitting into a lock. And this is possible because we understand the structure of atoms and molecules, and we can use that knowledge to design molecules that will bind to specific targets. And this has led to the development of life-saving medicines, like antibiotics, which kill bacteria by interfering with their cell walls, and antivirals, which prevent viruses from replicating, and chemotherapies, which kill cancer cells by damaging their DNA, and vaccines, which stimulate the immune system to recognize and fight pathogens. And all of these are based on our understanding of the atom and the science of chemistry. And it is a powerful example of how the atom can be used to heal and to protect. Now, let us reflect on the atom in the context of energy, because the atom is a source of immense energy, both in the form of chemical energy, which is stored in the bonds between atoms, and in the form of nuclear energy, which is stored in the nucleus, and chemical energy is what powers our bodies, our cars, and our power plants. It is the energy released when we burn fossil fuels or when we metabolize food. And it is the energy that we harness when we create batteries. And nuclear energy is the energy released when we split or fuse atoms. And it is the most powerful source of energy known to us, because it is the energy of the strong nuclear force, and it is the force that powers the sun and the stars, and it is the force that has created all the elements, and it is the force that we have harnessed in nuclear power plants and nuclear weapons. And this energy is both a blessing and a curse, because it has the power to provide clean, abundant energy, and it has the power to destroy. And it is a reminder that the atom is not just a passive thing, it is a source of immense power, and we must use that power wisely and carefully, with respect for the atom and for the world we live in. Let us also think about the atom in the context of technology, because technology is the application of scientific knowledge to solve practical problems, and our understanding of the atom has led to a revolution in technology. And this is particularly true in the field of electronics, which is based on the properties of semiconductors. And semiconductors are materials that have electrical conductivity, between that of a conductor and an insulator, and they are made of atoms like silicon and germanium. And the behavior of semiconductors is controlled by the arrangement of their atoms and the presence of impurities, which are called dopants. And by doping a semiconductor with different atoms, we can create regions that have an excess of electrons, called n-type, and regions that have a deficiency of electrons, called p-type. And when we bring these regions together, we create a p-n junction, which is the basis of diodes, transistors, and integrated circuits. And these are the components that make all of our modern electronics possible, from computers and smartphones to televisions and medical devices, and the entire information age, the digital revolution, is built on our understanding of the atom and on our ability to manipulate it. And this is a stunning achievement, that we have been able to take something so small and invisible and use it to create a world of communication and connection and innovation. And it is a testament to the power of the human mind to understand and shape the universe. Now, we must think about the atom in the context of the environment, because the atom is also at the heart of many environmental issues. And this is particularly true of pollution and climate change, because the burning of fossil fuels releases carbon dioxide into the atmosphere, and carbon dioxide is a molecule made of one carbon atom and two oxygen atoms, and this molecule absorbs infrared radiation, trapping heat in the atmosphere and causing global warming. And this is a classic example of how the behavior of atoms and molecules can have a profound impact on our planet. And it is also true of other pollutants, like sulfur dioxide and nitrogen oxides, which react with water vapor in the atmosphere to form acid rain, and chlorofluorocarbons, which break down the ozone layer, and heavy metals, like lead and mercury, which accumulate in the environment and cause health problems. And all of these are examples of how the atom, when released into the environment in the wrong way, can cause harm. And it reminds us that we are stewards of the atom, and we have a responsibility to use our knowledge of atoms and molecules to protect the environment and sustain life on Earth. Let us think about the atom in the context of the Earth itself, because the Earth is made of atoms, and its history is written in its rocks and minerals. And the rocks and minerals are composed of atoms arranged in crystalline structures. And the study of these minerals is called mineralogy, and it is a fascinating field because it reveals the history of our planet, the processes that have shaped it, and the forces that continue to act on it. For example, the rocks of the Earth's crust are made of silicate minerals, which are composed of silicon and oxygen atoms bonded together in tetrahedra, and these tetrahedra form the building blocks of many minerals, like quartz, feldspar, and mica, and the way these minerals form and interact is determined by the properties of their atoms and the temperature and pressure at which they form. And the study of these minerals has given us insights into the formation of mountains, the movement of continents, and the evolution of the Earth's atmosphere and oceans. And it has also given us the resources that we depend on, like metals, fossil fuels, and gemstones. And it is a reminder that the atom is not just a microscopic phenomenon, it is a macroscopic force that has shaped the very landscape of our planet. Now, let us think about the atom in the context of the solar system, because the solar system is also made of atoms, and it is a beautiful and orderly arrangement of planets, moons, asteroids, and comets, all orbiting the Sun. And the Sun is a giant ball of plasma, of atoms stripped of their electrons, fusing hydrogen into helium. And this fusion releases the energy that makes life possible on Earth. And the planets are also made of atoms, arranged in different ways. The inner planets, Mercury, Venus, Earth, and Mars, are rocky planets, composed of silicate minerals and metals, and the outer planets, Jupiter, Saturn, Uranus, and Neptune, are gas giants, composed mostly of hydrogen and helium, and the moons and asteroids are also made of atoms, and the study of the solar system has revealed the incredible diversity of matter that exists, from the frozen methane on Pluto to the sulfurous volcanoes on Io, and it has shown us that the atom is truly universal. The same elements that we find on Earth are found throughout the solar system, and the same laws of physics that govern atoms here govern atoms everywhere. And this is a profound realization, because it means that we are connected to the entire solar system, and we are part of a grand cosmic family. Let us think about the atom in the context of the galaxy, because the Milky Way galaxy is a vast collection of stars, gas, dust, and dark matter, and it is all made of atoms, and the atoms in the galaxy are constantly being recycled, born in stars, released in supernovae, and used again to form new stars and planets, and this cycle of birth and death is what drives the evolution of the galaxy. And it has been happening for billions of years, and it will continue for billions more, and our Sun is just one of billions of stars in the galaxy, and our Earth is just one of countless planets. And yet, the atoms that make up our planet and ourselves are the same atoms that have been in the galaxy since its formation. And this is a humbling thought, because it means that we are not just citizens of Earth, we are citizens of the galaxy, and our atoms are part of a great cosmic tapestry. And when we look up at the night sky, we are seeing the light of billions of stars, and that light is emitted by atoms, and it carries information about those stars, and it connects us to the rest of the galaxy. Now, we must think about the atom in the context of the universe, because the universe is the largest and most comprehensive context of all, and it is made of atoms, and the universe has been expanding and cooling since the Big Bang, and as it has cooled, it has allowed atoms to form and coalesce into the structures we see today, and the cosmic microwave background radiation, which we talked about earlier, is the oldest light in the universe, and it was emitted when the universe was only about 380,000 years old, and it is the light of atoms, the first atoms that formed after the Big Bang, and this light tells us about the composition and evolution of the early universe, and it tells us that the atoms that make up our bodies were forged in the hearts of stars, and that we are truly children of the cosmos. And this is the deepest and most profound lesson of the atom, that we are not separate from the universe. We are the universe. We are a part of it, and we are a way for the universe to understand itself. And this is a beautiful and peaceful thought, and it is a thought that we can carry with us as we drift off to sleep, knowing that we are connected to everything that has ever existed, and everything that ever will exist. Let us think about the philosophical implications of the atom, because the atom has inspired deep thought about the nature of reality, and it has challenged our assumptions about what is solid, what is real, and what is fundamental. For example, the atom teaches us that the solid world is not solid at all, that it is mostly empty space, and that what we perceive as solidity is just the electromagnetic force repelling our atoms. And this is a profound insight, because it shows that our senses can be deceived, and that reality is not always what it appears to be. And the atom also teaches us about the nature of identity, because an atom is not a permanent thing, it is a temporary arrangement of particles, and these particles are themselves not permanent, they are constantly interacting, changing, and sometimes transmuting into other particles, so an atom is more like a process than a thing. And this is true of everything, including ourselves. We are not static beings, we are dynamic processes, constantly changing and evolving. And the atom also teaches us about the nature of connection, because atoms are always connecting to other atoms, always bonding and interacting, and nothing exists in isolation. Everything is connected. And this is the most important lesson of the atom, that we are all connected, and that we are all part of a vast, interdependent web of being. Now, as we approach the end of our journey, let us reflect on the beauty and the poetry of the atom, because there is a deep aesthetic quality to the atom, a kind of hidden beauty that we can perceive when we understand its structure and its behavior, the electron clouds, the energy levels, the spectral lines, the molecular structures. All of these have a kind of elegance and symmetry that is pleasing to the eye and the mind. And this beauty is not just superficial, It is a reflection of the deep order of the universe, the elegance of the laws of physics, and the ingenuity of nature. And when we look at a crystal with its perfect geometric shape, we are seeing the beauty of the atom at the macroscopic scale. And when we look at a flower with its intricate colors and patterns, we are seeing the beauty of the atom expressed in the dance of life. And when we look at a starry sky, we are seeing the beauty of the atom shining across the cosmos. And this beauty is a source of wonder and inspiration. And it reminds us that the universe is not just a cold, mechanical place. It is a place of profound beauty and mystery. Let us also think about the future of the atom, because the atom is not just a thing of the past, it is a thing of the future. And scientists are continuing to explore the atom and its potential, and they are making new discoveries that are pushing the boundaries of our understanding. And they are developing new technologies that will change our world in ways we cannot yet imagine. For example, quantum computing, which we touched on earlier, is a technology that harnesses the strange properties of atoms, like superposition and entanglement, to perform calculations that are impossible for classical computers. And this could revolutionize everything from medicine to artificial intelligence to materials, science, and nanotechnology, which is the science of manipulating atoms and molecules, is another emerging field, and it has the potential to create new materials, new medicines, and new devices. And it could even lead to the creation of molecular machines, tiny machines that can operate inside the human body. And these are just two examples of the future of the atom, and there are many more, and it is an exciting time to be alive, because we are on the brink of a new era of discovery, an era where we will harness the full power of the atom to improve our lives and understand the universe. And this is a peaceful and hopeful thought that the future is bright with possibility. Finally, let us think about the atom as a symbol, because the atom has become a powerful symbol in our culture, representing science, technology, and the interconnectedness of all things. And it is a symbol that reminds us of our potential, our curiosity, and our desire to understand the world around us. And it is also a symbol of peace, because when we understand the atom, we understand that we are all made of the same stuff, and that the divisions that we perceive between ourselves and others are just illusions. And this is a message of hope, a message of unity, and a message of compassion. And it is a message that we can carry with us in our hearts as we go about our lives, and it is a message that can bring us peace in a world that is often chaotic and confusing. And so, as we bring this long and gentle journey to a close, let us hold on to the atom, this tiny, invisible, and yet incredibly powerful thing. And let us remember that we are made of atoms, and atoms are made of dreams, and dreams are the stuff of the universe, and that we are all part of this great cosmic dream, and that is a beautiful and peaceful thought to carry with us as we drift off to sleep. Thank you for joining me on this journey. Thank you for your patience and your curiosity, and I hope you have found peace and relaxation in these words. May your dreams be filled with the gentle glow of atomic light, and may you wake up tomorrow feeling refreshed, connected, and full of wonder for the incredible universe that we inhabit. Good night and sleep well, knowing that you are made of atoms, and atoms are made of dreams, and those dreams are the universe dreaming of itself.